Do I have any food on my face? No, it's fine. Okay. Hope everybody had a good lunch. I miss the lunch buffet at conferences. It's always very nice. You have to queue for 5 minutes. So I decided this time I'm going to queue in my own kitchen for 5 minutes, put my food on a paper plate. I thought it was going to be in the spirit of the conference. And I wanted to chat with Benjamin, but unfortunately he was too busy finishing his slides. So now, Benjamin,
hello, Sebastian.
He's going to talk on the API monitoring and tooling slot, and he's going to introduce his tool that he did to monitor an AWS EC2 instance. Hello, Benjamin.
Hello, thank you, Sebastian. And thanks to the Apidays team for setting up this sustainability track. So I'm Benjamin Davy, and I work for Teads. Teads is a digital advertising company helping news publishers monetize their content by delivering ads in a respectful way. And here you can see moving an example of our ads displayed inside an article. So why did we do this, build this dataset for EC2? Well, we wanted to know more about the carbon footprint of our service and discovered that there was a lack of resources on that topic. So we tried to see if there would be a way to estimate it using a bottom-up approach, starting with compute resources. So where can we start? Here you can see an overview of the main moving parts involved for our advertising service. All these are generating impacts from the cloud data center to the network infrastructure and the device displaying our ads. And today there is no standard methodology or even emission factors to assess a digital service like this one. And when I'm talking about emission factors, I mean having the carbon emissions related to the computing and networking activities we are generating. And as our main provider is AWS and the main service we use is EC2, we started by having a look at how we could estimate the impact related to using cloud instances. If we have a look at the main components of a data center, we can see that the compute resources we are trying to estimate are only a part of all emission sources. But if we focus on the EC2 service, we can simplify by saying that the emissions come from two main sources. The first one is related to running the servers supporting the EC2 service. And for this, we need to know the power consumption and the location of this hardware. And the other important source of emissions is the manufacturing of this hardware. Now, let's start with emissions related to running our instances. In order to estimate them, we need to find a way to know the power consumed actually by our instances. We also need to know the power usage effectiveness, also named PUE, of the data center. This basically tells us the power used for things that are not IT equipment in the data center, like the cooling systems. AWS communicates that all their data centers have a PUE under 1.2. It means that if our server consumes 100 watts, we can add 20 watts to cover for all the things around it that are required to run our machine and consuming power. Once we have the power consumption, we need to convert this value into carbon emissions. For this, a first option is to use available electricity carbon emission factor per country. And looking at this, what we didn't have at all to build our dataset is the actual power consumption of instances, and actually there is a way to estimate it. Let's see. So on modern Intel CPUs, we have access to something called RAPL, running average power limit, an interface that gives access to a set of counters, giving energy and power consumption information. The first problem is that it's only accessible on bare metal machines. But the good news is that we have access to some on AWS. Using Turbostat, a tool that we see here, written by Intel, we are able to get the information we have right now. So what do we get? First, we get the CPU TDP that was underlined in red on top, which stands for thermal design power. According to Intel, it refers to the power consumption under the maximum theoretical load. So it's supposed to be the maximum sustainable power consumption for the CPU. And this is especially useful because on AWS, the machines we use CPUs that are custom made, which means that even if we can get the CPU model using a simple ls-cpu command on the terminal, we will never find any public information about this CPU model online. But most importantly, the tool gives us access to the power consumption for the CPU and the memory of the machine. So this is what we have on the right downside, the package watt and RAM watt. On a side note, we have to keep in mind that this relies on some sort of software modeling, and it's not as accurate as a physical power analyzer. So it's a first limitation. So in order to build consumption profiles, we combine two tools. The first one is StressNG that we use to create a stress protocol to simulate different usage contexts. For example, a CPU or memory-intensive workload. And we use turbostat to read the power consumption during the test. The resulting tool is called TurboStress, and you can find it on our GitHub. Let's now see some results. So here we compare 3 different C5 metal machines running in different regions. The one in dark blue on the graph was actually running with underclocked CPUs, and we can see this reflected in the lower power consumption values. So on the chart, we have the overall CPU plus memory consumption for different stress tests, and first for the idle state. We have several tests for which we set a target CPU load, and then 3 additional tests that are supposed to stress the machine to its maximum. So for a C5 that has 2 Intel CPUs and a fair amount of memory, we can see the power consumption reaches more than 900 watts to its maximum. We've continued this test campaign and collected the results for all available Intel bare metal machines to build a power consumption dataset. It was already a satisfying result. However, it has many limitations. First, we couldn't do this for instances using AMD CPUs as there was no bare metal machines available. And also, this power consumption feature doesn't have an equivalent on ARM CPUs, so we can't test Graviton-based machines as well. Another limitation is that doing this, we are only measuring part of the server, the CPU and the memory. And finally, this is a bare metal measurement, and like many AWS customers, we don't use bare metal machines at Teads. So this was not directly usable. Now, the CPU and memory are supposed to be the main power drivers of a server. However, there are other parts that are consuming power as well, such as the main board, fans, storage, drives, network cards, additional cards and drives, etc. In another test, we ran our tool on-premise and compared the result with the power supply consumption that was reported by the server. This was still not a perfect measurement, but at least it covered the whole machine. On the chart, we see the difference in yellow. That should be the power consumption of the rest of the machine. And it looks like the CPU and memory are indeed the main power drivers for this type of hardware. We did several analyses and chose to define a value that we add on top of our measurement to cover for what we cannot measure. For now, it's simply a percentage of the CPU TDP. Next, now that we are able to get an estimation for an entire physical server, let's see how virtual machines are defined by AWS. As stated here, on most instance families, there is no overcommitment, which means that resources you get, vCPUs and memory, are dedicated to you. Also, hardware resources are cut into virtual instances in a linear way, which simplifies our work. It means that based on the bare metal consumption profile we built, we can roughly estimate the consumption of an instance. In reality, this is not that simple, but we considered it good enough for our estimation. In the case of AMD and ARM platforms that we couldn't measure, we generalized our previous results based on the machines and CPU known specifications. So as an illustration, we can say that a C5.12x large machine instance, will be the equivalent of half a C5 bare metal machine. We calculated this power consumption for 4 load levels for each bare metal configuration. And since we consider that these bare metal machines are simply cut into instances, we apply a ratio based on the number of vCPU available on the instance and compare it to the bare metal platform. So for our example, that is half of the C5 metal, we get the following consumption profile. So here you can see the 4 levels from idle to 10% load to 100% load for the C5.12x large, which is half of what we have on the C5 metal. Okay, so moving on to the second emission source. Let's see if and how we can estimate the carbon footprint of manufacturing the servers used for the EC2 service. And actually, this is an even more complex challenge. If we take our instances, we are able to retrieve some information about the underlying hardware, but some parts like Nitro cards that are custom made by AWS are not available anywhere else, so it could be hard to compare with known products. And also, there isn't a lot of information about the manufacturing footprint of IT equipment to compare these specifications with. Some manufacturers, like Dell, provide a product carbon footprint document for their machines. Here you have the manufacturing footprint on the last column for different server configurations. Unfortunately, this is not ideal because the specifications used for these product carbon footprint are not comparable to our AWS servers. For example, the amount of memory on these machines is ridiculously low. Also, there are really few examples where the impact is detailed at the component level. So we don't really know how a specific component could impact the manufacturing footprint. We've also looked at other publications, and you can check our article if you want to know more about this part of the study. So looking at the few data available, we came up with this naive model to estimate the emissions from manufacturing. We defined a minimal server with 1 CPU and a low amount of memory and assumed it has a manufacturing footprint of 1 ton of CO2 based on the literature we found. Then we set other carbon footprint values for additional parts we can have on AWS machines. But for some parts like GPUs, we didn't find any data. So the 150 kilograms of carbon emissions related to a GPU card is kind of a wild guess. Also, we define only 1 value per type of component, even if the actual manufacturing footprint can vary a lot between 2 different parts. So it's indeed a very first and naive estimation. Anyway, we applied this model to each bare metal platform we have on EC2, and we considered that a server could have a lifespan of 4 years, which is the value used by most manufacturers, and we computed an hourly rate for these emissions. Here you can see some examples for instances that rely on a hardware platform equipped with GPUs, some with local storage, etc. For each additional part, we add some emissions before calculating an hourly rate at the instance level. Good. So now, combining the two emissions estimations, we are able to compute an overall footprint. And here is a screenshot of a calculator we put online. You can select an instance, its location, and a number of hours to get an estimation. The result will highly depend on where the server is running. However, it's important to have in mind that the impact from manufacturing IT equipment are wider than simple carbon emissions. Here I mean water usage and material extraction, for example, that are required to manufacture the different parts included in our server. So looking at the carbon emissions is an important and interesting step, but in the end, it's not enough. Anyway, this tool and this dataset can be used for a granular analysis of our infrastructure, even if it's not perfectly accurate. You can get all the resources related to this session on our website with the full methodology, the dataset, and this calculator on engineering.teads.com. And we are really looking for feedback, so please do not hesitate to contact us. And before wrapping up, I wanted to mention two other open source initiatives. The first one is the Cloud Carbon Footprint project that converts billing data into carbon emissions and that supports Azure, AWS, and GCP. It does not yet support manufacturing emissions, but it's on the roadmap. So I really suggest you have a look at it and maybe help contribute to build this tool. And the other one is Scaphandre, and you can stay here with us as it will be presented in the next session. Thank you for your attention, and yeah, bon appétit if you are eating.
Thank you, Benjamin, and a great way to introduce the next session. But first, let's start with a few questions. You mentioned that you were expecting, I mean, you were looking for feedbacks. Is there a particular type of people you're looking feedbacks from, like cloud providers or industry, you know, from the industry of servers? Is it anybody in particular?
Obviously, having feedback from providers would be really nice to see if these estimations are in the right order of magnitude. But also looking for feedback from the community that could use this information to build some tools to monitor the impact of their infrastructure and help find ways to reduce the impact. Really looking forward to that.
Okay, and other questions from Jérôme on the chat. He's asking, did you already compare your outputs with the Amazon CO2 calculator?
So the AWS calculator is not globally available yet. And from what we know, it will be something similar to the GCP report, customer report, or Azure customer report. And these should give you an overall footprint for maybe per month for your compute service for EC2, for example. So it would be hard to compare one big number for the month with a dataset on the instance level. And also, these reports usually do not report the manufacturing emissions, only the emissions related to the use of electricity. So it's difficult to compare.
Mm-hmm. Okay. And another question from Antoine: which links? What are the links with other initiatives like Boa Vista, Etsy, and AWS itself? Have you talked to AWS?
Sorry. So, is there other initiatives?
No. Do you have any links with other initiatives like with Boa Vista? We'll talk more about it in a few.
Yeah, there will be another session.
With Etsy, have you been in contact with Etsy? Have you been in contact with AWS?
I suggest you check engineering.teads.com. We have a sustainability section, and we link all the initiatives we are part with, and some resources, so you can check that.
Brilliant. Okay, Antoine is doing a little bit of advertising, you can see on the chat. Another question for me, another question from Nicolas, which I lost, so I'm going to go back. Is it always a good idea to migrate workloads to the latest and more efficient instance generations?
So it's a bit of a tricky question. So if we have a look at it from only considering the electricity usage, you can think that using the latest hardware will give you a better efficiency, so more performance for the same amount of electricity used. But if you also consider manufacturing this new hardware and reducing the lifespan of the hardware globally, it might be a very bad idea, because the impacts of manufacturing are really important, and maybe worse on some point to only carbon emissions.
Okay, thank you.
It's a bit tricky.
Yeah. Okay, thank you for that. I mean, we've talked this morning with Google, we've talked with Scaleway. They're all introducing new carbon reports, and it's brilliant. And it's going to make the whole industry move forward. But do you think it's enough? Is there something more to do?
More transparency is always better. And what's lacking today is a common ground for all these initiatives. Having a standard for all providers to report the same thing, the same parameter, using the same metrics is, I think, what is lacking the most. We might see a lot of calculators coming out, but it will be difficult to compare two reports from two different providers because of that, because they are not based on the same methodology. And it's not their fault, it's a problem of standard, I guess.
Mm-hmm. Do you see anything moving towards standards in this area, or?
There are things in some countries. So in France, we have a lot of things moving with the French Agency for the Environment and Climate Change. There are projects, but and there are also initiatives from other organizations, but I'm not familiar with anything that would bring quickly a standard usable by all providers.
Okay. And final
yes,
question.
SDIA, I'm seeing in the comments, the SDIA is trying to do that, but it would need to be embraced by the cloud providers to be great. But yeah, there are many great initiatives.
Thank you, Simona, for pointing that out. My last question would be, what do you think you're going to do at Teads with this information? What's your next step?
So the next step is to do different ad hoc analysis of different services. Check also how old is our infrastructure. So in the dataset, we have listed the release date of each instance type. So it could be interesting to also see if we can correlate how old our infra is, how much it consumes, and if we improve, how does this change along the way. But yeah, mostly to add new monitoring on this metric.
Okay, Perfect. Well, thank you so much, Benjamin, for your talk, and hope to see you soon.
Thank you.
Bye-bye.